Okay, so let's start talking about some of these bitwise operations that many of you maybe have not seen since like CSC300 when I introduced some stuff. So let's kind of go back, and when I say I want to just review on what this idea of bitwise means. Anybody want to take a stab? When I say bitwise, what am I talking about? This is kind of like one of those vocabulary words that might be beneficial in in a conversation in the future dealing with digital stuff. Go ahead. All right, so we're definitely talking more closer to the machine level, but specifically the, well, what does the word bit mean? So bit means a single 0 or 1. We're all good with that? That's what a bit is. All right, so now when if I say measure something lengthwise, I'm kind of telling you to measure it by its length, correct? So when I say bitwise, that means we're going to be doing something on a per bit basis, not using an entire number, but maybe a portion of a number. And then we want to even change our mentality of, and I'll show you what I mean here in a second. We want to change our mentality of what a memory location can actually hold and pull this back into real life. So how many of you in here have had CSC325? Computer organization class? All right, how many of you are taking it in the spring? A couple of you. I'm not sure if I'm going to be teaching that. Usually Dr. Locklear teaches. I teach our graduate one, but he's on sabbatical next semester, so you might get me for in there. But in any case, those of you who've had 325, you probably found the class to be somewhat cryptic, right? So it's just like any of these other things. And if you've had my classes, more than one of my classes, which most of you have, I always come back to this stuff that a lot of times in technology, we make easy things sound difficult because they're so different than they are. They sound like they're very different to how we might do things in real life. Correct? When the reality is they're actually the same thing, and almost always easier with technology. They just sound scarier. So we're going to look at a couple of examples with that as well. So as a starting point, let me do something you may have bumped into at some point in your travels. So if I come out here. Oh, thank you. I wonder why that is. Oh, it literally just changed. Okay. Let's actually just do this. Let's see if it just we'll try the default source. I feel like there should be. Okay, there we go. Yell at me if it happens again, please. All right. Usually log in with GitHub. All right. So what I'm going to do here just for a moment, let's go to my projects. Give myself a little empty screen here. Now, if I say int b is equal to 5 and 3. And I say print out the value of b, I get a 1. So the question is why did I get a 1? If I say 5 or 3, I get a 7. So to somebody who's never worked with Bitwise stuff, you might look at that and say, okay, what? What's going on there, right? All right. So this ultimately comes down to, what is this guy? When we see the vertical bar, we typically are thinking about the OR operator, right? Ampersand is ands, vertical bar is ORs in our C-based languages. Okay, but usually we see 2 of those guys. And maybe way back when you first learned it, you might say, why 2? Wouldn't it be easier if I only had to type one of them? Well, one of them was already taken. And it's called a bitwise operator. It's for doing things on a bit by bit level with numbers, let's say. Now we're going to be answering today the why. Why would we want to do that? This is how we do it. Okay. Now inside of a computer, if we're storing the number 5, computers like things in binary, right? So we're probably not, 5 right now is represented as a decimal value. 3 is represented as a decimal value for us, right? But inside the computer, if I do something like 5 or 3, this is actually going to be the binary version of 5. So that's going to be 101 or, and then 011. So this says the exact same thing, isn't it? Isn't that identical to this? This is just happens to have our values represented in binary instead of base 10. We're all good with that? Okay. It's still the exact same number. 101 in binary is the exact same magnitude as the value 5 in decimal. French versus Spanish, just 2 different ways of representing the same value. Okay. So now when we talk about bitwise, if we're doing a bitwise OR on these guys, what I'm going to do is I'm going to go bit by bit and do an OR on those bits. So a 1 is true, a 0 is false. So 1 bitwise OR 0, that is this first 1 against this first 0, with an OR, only one of the 2 values or both of them have to be 1. So 1 or 0 is 1. 0 or 1 is 1. That's this 0 right here, and that's this 1 right here. 1 or 1 is 1. Make sense? So if you had written it right on top of each other like this, you would have gotten that if you applied OR to it. And what is this value in decimal? A 7. 5 bitwise OR 3. 5 bitwise OR 3 gave us a 7. If I do the same thing with an AND, exact same thing is kind of going down. Oops, sorry. But now we are doing ANDs here. So for an AND to be true, both need to be 1s. 1 and 0 is 0. 0 and 1 is 0. 1 and 1 is 1. So that is 001 or a 1. Change this to an AND, run it again, we get a 1. Okay, so we understand why we're getting that output now. We're all good with that? Okay. We don't know why we might do that. We just know that we can do that, and that's what's happening. All right, so any questions about that side of things right now? Okay, and so the idea that we did things on a bit by bit basis, this idea of bitwise operations, now also makes sense, right? We're diving down, like you pointed out, we're kind of close to the computer. We're doing things, you know, kind of near the hardware or something like that. All right, so let's now look at our other bitwise operators. So I've looked at a bitwise and a bitwise or, and I probably have some other examples there, but we just went through it. Let's look at these left and right shifts. Now, those of you who had 325, you looked at the bit shifts in there, didn't you? Okay. So what does a left shift do? What ultimately is it accomplishing? Go ahead. Okay, yep. So if we had a bunch of bits, it shifts everything to the left, killing off the guy down here and giving us a new dude over here, right? Actually, it won't even kill it off. It just shifts it. So if you have 1, 1, 1 and you shift it left, you'll have 1, 1, 1, 0. Make sense? And what did that ultimately do? It multiplied by 2. Because we shifted it by 1 power of 2. All right, right shift does the opposite, correct? Right shift shifts everything to the right, which will kill off the guy on the far right, giving you an extra padded 0. Divide by 2. Okay, we'll see some examples here. So if we have a left shift, 1, 0, 1, 1, and we left shift it 1 time. So let's go into the code here. And let's say 5 left shifted 1. Oh, I didn't have a semicolon at the end of it. There's our 10 multiplied by 2. If I left shift it 2. There's our 20 multiplied by 2, then multiply by 2 again. But let's see what's actually happening when I say 5 left shift 1. Ones, twos, fours, eights. So this is actually the this is the number 11. So if I start with the number 11 left shifted 1, we should get a 22. So there's our 22 multiplied by 2 because we left shifted. So what's actually happening here is the number 11 in binary, correct? So the decimal number 11 can be represented with the identical magnitude in binary as 1011. Then if I use the bitwise left operator, and this says, the second number says, how many times do you want me to shift left? In this case, I'm just shifting left once just to show this. So that means I started off the 1011. I shifted it to the left, opening up a new kind of empty bucket here. Because I moved it to the left, and now in the ones place, we have a new empty bucket. So that becomes, we didn't add to the magnitude there at the ones place, but we still needed to fill it out. Our 4-bit number just became a 5-bit number. All right, because we did increase the meaning of that bit. That bit used to be in the 8s place. Now he's in the 16s place when I shifted him to the left. All right, make some sense? Okay, still, we haven't gotten to the why would I ever want to do this. We're just looking at the, this is how it works if I were to play this stupid video game. Okay. So, and ultimately the left shift does what? It multiplies the base value by 2. Similarly, if I do a right shift, we get a, this is integer division, right? 11 divided by 2 is 5, remainder 1. So this gives me the quotient of 11 divided by 2 in integer division. So here's my same number 11. I right shift it. Technically, this did become a 5-bit number if we want to think about it like that. So when I shifted it to the right, this dude fell off. This far right one fell off into oblivion because he was already in the ones place and there's nothing to the right of the ones place. So he fell off the face of the earth and now he's no longer part of it. We can think of it like this value just expanded. We got an extra spot, right? Which we can fill in with a 0. We can say, oh, okay, so now our 4-bit number just became a 5-bit number. I can put 4,000 zeros on the left side here. It won't change the value of this number, right? Okay, so, but if we want to say whenever we're dealing with shifts, we are increasing the number of bits by 1. A left shift would increase the number of bits on the far right. A right shift would increase the number of bits on the far left. All right, but it's always adding the new bits as a 0, which they don't change the value in that base. But with a right shift, I mean, I can just sit there and hang out on the 0 key here, and that number is not changing its actual decimal equivalent at all. Make sense? All right, so when I take 1011, I right shift it once. I'm left with something like this. This is the 1's place, the 2's place, the 4's place. 4 plus 1 is 5. This is the integer division of that guy. Right, and the dude that was lost was my remainder. All right, questions about right and left shifting? Now, hopefully we're starting to maybe question, like, okay, this is all fine and good, but what does this have to do with our priority queue? What does it have to do with our heap? We'll get there. Presumably, we're going to have to use some of these things to work with our heap to get us to where we actually want to go. All right, we already looked at the bitwise and the bitwise or. We're all good there. So we're all familiar now with our 4 different bitwise operators in this current world. Because there's technically a bitwise XOR as well, which is an exclusive OR. I can say 5 XOR 3. And I get that. See, that this is actually a good one, because most people look at that and say, oh, you want to take the 5 to the 3rd power, right? But what I'm actually doing is I'm performing an exclusive OR on the bits. If I just add that's probably the more common thing you might bump into, trying to do that in code and you get the wrong answer. So a 5 is 101. A 3 is 011. A bitwise OR says perform a OR at the on a per bit basis. And a bitwise OR says 1 or the other, but not both. So 1 XOR 0 is a 1. 0 XOR 1 is a 1. 1 XOR 1 is a 0. It can't be both with an exclusive OR. A normal OR, a 1 or 1 is a 1. But an exclusive OR, a 1 XOR or XOR 1 is a 0. It can't be both of them. So this is 110 or the number 6. Make sense? And that's what we got right here is a 6. Where a programmer who might say, oh, I'm used to putting this when I want to take something to the power, is not expecting a 6 when they want to put 5 to the 3rd power in there. They're getting a strange value. And they might wonder why, and it's because they don't know about bitwise operators. Okay. So now let me talk about memory storage stuff a little bit, just to kind of put this stuff in context of why generically, before we talk about how we're going to actually use this with our heap, why generically might I want to use these ands and ors and shifts and things like that to do stuff certainly at the computer level. So in our computer, we have these things called hardware registers, right? Okay, what's a hardware register? When I say that, what am I talking about? 325 people should have this answer. You forgot, but you talked about it, right? Okay. Well, we all know what memory is. What's memory? We've been talking about memory in this class a lot with all our pointers and crap like that, right? So what's memory? If you had to give me a generic definition for memory, what would you say?
Temporary place for data that needs to be processed.
Okay. Place to store crap, right? So this is something in real life, right? So how many of you have backpacks in here? Everybody brought a backpack? Yeah, why do you have a backpack? Carry your stuff, okay? So you have a little portable bucket of memory that you brought with you. Just make sure. Okay, that's fine. You have a little portable bucket of memory that you bring with you to throw some stuff in that you need direct access to while you're out and about, right? Because if you left something, because you have other storage things in your life, right? So back at your, maybe some, how many of you use your car for some storage stuff? Passenger seat, back seat, all of the above, trunk. My wife says I have a hobo living in my car. And when I was using her car when mine was in the shop, she said my hobo had moved into her car. Stores of stuff in there. But so when you have your stuff that you have in your car, how many of you have cars here on campus? A couple of you, okay. So you have some stuff in your car. And have you ever been in a situation where you need something that you wish was in your backpack, but you actually left it in your car? And now it's like, okay, well, am I going to go and spend the 5 minutes or whatever to retrieve it? Or am I just going to do without it? All right. So that backpack's your hardware register. If you're the CPU, you're the one operating yourself here in real life, and you need things that are right there available to you. You might say your pockets are kind of like your hardware register, but whatever. Storage that's very, very, very locally accessible to you would be like a hardware register. That's a piece of memory associated with the processor that is quickly accessible. You can get to it quickly. Your car might be like your like L1, L2, L3 cache. Our processors have, you certainly have more space in your car than you do in your backpack or you do in your pockets. So maybe we could say your pockets is like a hardware register. Your backpack is like L1 cache, or any of the caches. And maybe your car is system memory, right? So that means that you can get to your pockets real quick. You can get to your backpack with a little more effort. You got to start unzipping things and stuff like that, but it's still convenient. But if you got to go all the way to your car, that's going to take some time. Okay, then we're just going to keep the analogy going. Maybe your apartment, your house, whatever. That's kind of like your hard drive. Maybe you have stuff there you can store. It's lots more space there. Okay, but way less convenient to get to right now, especially if you live off campus. And because if you're on campus, then you actually might be able to get to your dorm faster in your car. But I think you get the point here, right? We have various places to store crap, and depending on how close those places are to us, they probably become smaller and smaller to make us be able to carry them. But they also make those things, the things we put in there are things that we need to have very convenient access to. All right. You're probably not bringing like your, I don't know, like a tow rope in your backpack. Hopefully none of you have a tow rope in your backpack. Something you only need every blue moon or something like that. You're not bringing that for nice convenient access in your backpack. Okay, so when we're talking about hardware registers, and this is really, you could replace this with anything that is memory. Okay, but hardware registers become, I think, a very interesting thing because I'm trying to connect them to like your maybe your pocket, since it's a small location. You can only fit so much stuff in your pocket, right? All right. Now, for the sake of this argument, since we're talking about this idea of hardware registers, let's say that without getting clever, we can only put one thing in our pocket at a time. So let's say I take out a quarter and I hand you a quarter. Do all of us have pockets that could easily hold a quarter, assuming you're wearing something with pockets? A quarter easily fits inside of a normal pocket in clothing, right? You'd have some extra space in there, right? So if I tell you can only store one thing, you would say storing a quarter in your pocket is pretty wasteful. It's accomplishing the job it needs to accomplish. But you got some more space in there where you could fit other stuff. But if I asked you to retrieve a quarter and you had a single pocket, single hardware register that you put a quarter into, you could just haphazardly reach your hand in there, grab whatever is in the pocket, pull it out, and there's the quarter. You don't need anything special, no special ninja moves in order to extract that quarter from that container, that pocket. What if I say, okay, you know what? You're now allowed to hold, let's keep it, let's say 2 poker chips in your pocket. Same size, but one's a red poker chip, one's a green poker chip. What I'm getting at there is you can't tell which is which when you reach your hand in there, right? So if I say, get me the green poker chip, what you really need to do is you really need to get the entire contents and then extract the element that I'm asking for from it. All right, make sense? So as human beings, we do this at home, don't we? You have drawers, and you might have a dresser of drawers at your house, and you don't have only one type of thing in a single drawer, or you don't necessarily have just one type of thing in a single drawer, right? Maybe you have your your t-shirts and your flannels or something like that in the same drawer. You have socks and underwear, same drawer, whatever it is. Kind of get where I'm going with this. And what you do is you're using one single storage location to store multiple things, but then a human being uses their eyes and things like that to determine, oh, if I need one element, I'm going to go onto this half of the drawer. If I need another element, I'm going to go to this half of the drawer. Or if you do the college organization thing, you have the pile, right? And you start fishing through the pile looking for what you want. Backpack's the same thing. In my laptop backpack, I've collected wires of various types over the years. So you need a charge cable. I'm going to have 40 options, and maybe we'll never find the one you actually need. Just pulling out cables oh, I didn't even know they still made these devices. Something that's just been in there for a long time. All right, so we're all on the same page now. We know what's happening. So if we drop back down to the computer level and we have this hardware register, a lot of times the hardware register might be, let's just use a 16-bit memory location on the CPU. Now, typically hardware registers come in different sizes. We usually have 16-bit, 32-bit, 64-bit registers. More modern chips might have a 128-bit register. Okay, but for our intents and purposes, kind of think you got some of those cargo pants that has the tons of pockets on it, right? So you got some smaller pockets, you got some bigger pockets and all this stuff, but you have a finite number of pockets. All right, that's how hardware registers work. All right, so you can kind of load yourself up with stuff as you're walking around the world, but you're going to put, maybe you have one of those iPad minis and maybe it fits in the actual, the larger pocket on there or something. So you'll put that in there. I've seen people put skateboards. You seen those? Put a whole skateboard in their pocket. It's a thing. This is a real thing. All right, so in any case, we're going to say, okay, I have, this is maybe one of my smaller pockets, a 16-bit register. You might say there's an 8-bit register, but typically on most of our modern processors, the smallest size register is a 16-bit register. Now, we can say, you know what, I can store a single value, because now we're kind of back to, in human beings, we store stuff, right? You open up your backpack, you got all sorts of stuff. we're talking about computers. We're going to store collections of zeros and ones in our pockets, in our hardware registers, okay? So if I decide to use the entirety of that pocket, the 16-bit hardware register to store a value, I can store a maximum size value, a maximum unsigned size value of 2 to the 16th power, right? So I can store values between 0 and 65,535. That's the size values that I can put in a 16-bit register. All right. So 16 ones is 65,535. 16 zeros is a 0. And everything in between is one of those other 65,536 unique values. Okay. Now, I could say, you know what? Rather than storing one gigantic 16-bit value, maybe I want to actually store 4-bit values. Maybe I want to store 4 hexadecimal hextets, right? So maybe I want to store A, B, C, D. These are 4 hextets in a 16-bit register. All right, makes sense? So a 16-bit register has 16 individual buckets. Each bucket can hold a bit. So an A is the number 10, right? So that's 1011, or I'm sorry, 1010. That's the number 10. So the far left 4 bits will hold 1010. Next to that, I'll put a little space in here just for us. I'm going to store an 11. A B is an 11. This is 1011. There's my 11. A C is my 12, 1100. And a D is my 13, 1101. This is 16 total bits. So I have put 16 bits in my pocket that's capable of holding 16 bits, correct? But I know, because of how I've utilized my pocket, that there's actually 4 separate values in there. So I've had to encode my values into the pockets. This is, we threw the 4 poker chips now, in our example here, we threw the 4 poker chips in our pocket. But now to get those values out, I'm going to have to take a look at them and extract the individual values that meet the right color. Human beings are really bright, so we can use our eyesight and things like that and go and find the right chip and pull it out. But in computers, we're now going to need the ability to get these pieces out. Presumably, we had to also use the ability to get them in to the right places, because I said, well, my A is going to go in these far left bits. The B is going to go into the 4 bits next to that. The C is going to go into the 4 bits less next to that. The D is going to go to the far right bits. But let's just assume, because it's the same way both directions, let's just assume we got them in there somehow. But now, let's say that I want to get that value out of there. I want to extract the value A from this 16-bit register. Now, when I read from that register, I'm going to be reading the entirety of the register. So if I just read the value from this register, this is going to be this fairly big number, right? This is the ones place, 2s, 4s, 8s, 16s, 32, 64, 128, 256, 512, 1024, 2048, 4096, 80, whatever it is. You get the point, right? So then you add it all up and you get, this is the giant number that register currently holds. But that's not what I put in there. I'm not using that register to hold one big number. I'm actually using this register to hold 4 smaller numbers. So if I just want to get this far left number, what do I need to do? I want to read from my register and just get this one value. The hint is you're only going to need the tools that we looked at today. Shifts and ands and ors. Go ahead. Shift to the right 12 times. Okay, so if I took this number, let's call this register, we'll call it AX. All right, so we're going to say AX right shifted 12 times. And that's going to get me that guy. And then if I read from that register, I'd get a 10. So we're good there. Okay, that one was pretty easy. What if I want to get this value? So we extracted the A. How do I extract the B? How do I get the B? I don't know, you tell me. I'm not asking you to figure out something the computer may or may not be able to do by default. I'm saying here's 4 tools that we just picked up from Home Depot. We got left shifts, we got right shifts, we got bitwise ands, we got bitwise ors. Use those 4 tools to extract the B from that 16-bit register. Go ahead. Shift it left 4 times. All right, so he wants to shift it left 4 times first. So we can say AX 4, then AX right shift 12. Okay. This actually would accomplish it. It's not the way I would have done it. But so he's going to take the original value, he's going to left shift it 4, which is going to give him 1011, 1100, 1101, and then 4s like that. And then he's going to right shift it 12 to turn it into that guy. And then read from the register. We got our number. Okay, that'll work. Okay, not the way I probably would have done it, and for good reason. Because we're humans and we're clever, he was able to look at this thing in its entirety and say, okay, well, ultimately, what do I want? I need to get this dude sitting in that place. How do I get him there without breaking the rest of the number? So he said, okay, well, because I know he's in the second chunk, I'm going to shove everything out of the way to my left. Then I'll shove everything out of my way to the right. Speaking the last, so it's the bull in the crystal shop or whatever situation. But hey, it got the job done, right? Okay. How else could we have done this? We're going to do a single shift move, and then we're going to do a single bitwise move, either an and or an or. And it's called masking. So what I could have done is I'm going to right shift eight times. So if I right shift this guy 8 times, I'm going to be left with that guy, right? So far, so good. That's what I'm left with if I right shift it 8 times for my original value. So this is the value I want. This is the value that I currently have. Now, then what we can do is we can do a and on this, which will keep the values the same. You know, we actually could have done it. So I'm going to do a bitwise and. Of that. And with zeros will always give me a what? Anything anded with a zero will give me a what? A zero, right? A bitwise and says both need to be ones. So it does not matter what value I had up here. If I'm anding it against the zero, I will be left with a zero. If I'm anding something with a one, what will I be left with? Whatever it used to be, right? So you might actually like this better if I do it this way. If I want this second grouping, I can say I'm going to and it with that, then right shift 8. When I do that initial and, this is called a mask. I say, look, I just want to keep that one portion. The second grouping, they're called nibbles, the second nibble of this 16-bit value. So there he is right there. But then I said, you know what? In order to get the correct magnitude, I need to get this guy here. Make sense? Because if I read from it right now, it's just some giant number still. He's not the actual set value. So then I'm going to right shift 8, which will give me that guy, which is my B. So I want to get the C from AX. This was an and with that. I'll take AX. I will and it. With that. And then right shift it 4. Get the D. I'll do AX anded with. And I could say I'm going to right shift it 0, which means don't right shift it. You have your value. That make sense? So that's how we can use the shifts along with a mask, and using a bitwise and with the mask allows you to erase all the stuff you don't want and preserve the portion that you do want. And then the shifts allow you to position the portion that you wanted at the far right, so that when you actually read the value off it, you're getting the right magnitude. You know, that this is the first 4 bits. So it's the 1s, 2s, 4s, 8s place, and not like we're down here in the 64s place, even though I technically had the correct 4 bits of values. I need to get them positioned correctly. So when I go to read my number, I get the right number. All right, does that make sense? So now we're giving a little bit of rationale to why we might want to use bitwise operators and shifts. I might want to be more human with how I store crap in my pockets. I might not want to just put a single value in there. A lot of times I do. A lot of times, like, look, I need to, he kind of mentioned at the beginning, look, I need to temporarily store a number, and then I'm going to need it again in a minute. I don't care if I'm wasteful. I'm going to toss it over there, and then in a minute, I'll grab the value. I don't have to do any shifting or anything like that. I just have my value, and I'll go and do some mathy stuff with it, and I'll move on with life. That's fine. That might even be the normal go-to move. Okay. You know, but it's plausible that if you have a big enough pocket, you might try to put 2, 3, 4, 5 things in there. And as long as you kind of know what the capacity of the pocket is, you can kind of organize it in there. Now, human beings, we can be, you know, much more malleable with it. We could say, well, I'm going to put this tiny value here and a bigger value there. We can kind of mix and match, right? And then pull it out however we want. But computer, we got to be a little bit more algorithmic with it. He's like, look, I'm gonna divide this up into equal size chunks. That way I know what I'm dealing with when I go to pull it out. And then we'll put the values in there, however I'm going to put them in there, probably load it in, shift it across, that kind of stuff. And move on with life. You actually would have used bitwise ands and ors to get the value in. You bitwise them by each other, and that gets the value in. And then you bitwise it to map against the original to get you back to your original value. All right, so now, but we have a rationale as to why we might do this. Make some sense? We're good with that? All right, so that sets us up for next class, where we're going to look at, remember our goal here is to find the next open spot here. And we're going to use these bitwise operators to take us down, effectively use them as GPS. Do things to individual bits to say, well, do I go left or do I go right? Now I'm here. Do I go left or do I go right? Now I'm here. Do I go left or do I go right? Now I'm here. I'm at my destination. That's where the thing should go, using these same operators. All right, make some sense? All right, so we'll pick up with this slide next class. So no homework for Wednesday, but make sure you understand that bitwise stuff. I would say slight threat of a quiz on Wednesday. I'm not necessarily planning on it, but if it doesn't seem like you know what you're talking about when I'm asking questions in class, then we might have an impromptu quiz mid-class. We'll see. All right, I'll see everybody on Wednesday.